Okay, I wanted to finish up section 9.2. We're looking at graphing polar equations, and I had a list of 12 equations. We've looked at 10 out of the 12 so far, so I wanted to cover these last two and then also talk about some things on the calculator. All right, problem 11 is where we want to graph r squared equal 4 times sine 2 theta. So I'm going to start by making a table of numbers, and then I'll check if there's any symmetry. By the way, I guess I could know right away that this graph is going to be symmetric to the pole. Here's my polar symmetry test. If I replace r by a negative r, and I get the same equation, I'm going to have something that is symmetric to the pole. Symmetric to the pole means that you're symmetric to the origin. Well, I can see that right away here, right? If I replace r with a negative r squared is the same as r squared. So I'll get the same equation as I originally started off with there. All right, well, if I let theta be pi over 6, 2 times pi over 6 is pi over 3. Sine pi over 3 is root 3 over 2. Times 4 would be 2 root 3. If you have r squared equal 2 root 3 and you take the square root of both sides, then r would be equal to plus or minus the square root of 2 root 3. Okay, and if you go to the calculator and type that in, the square root of 2 root 3 is about 1.9 if you go nearest one digit on that. Okay, of course I got the plus or minus there, right? So on the pi over 6 radial line, I need to go 1.9 units. Also go in the opposite direction, 1.9 units, and plot that other point. Okay, and how about if theta is pi over 4 next? 2 times pi over 4 is pi over 2. Sine pi over 2 is 1. Times 4 is 4. R squared equal 4 means that r would be plus or minus 2. Okay, so on the pi over 4 axis, go out 2 units. Also go in the opposite direction 2 units. And of course, for any theta value I select, I'm going to have a plus minus deal here. So there's, there's going to be 2 points that I'll need to plot. If theta is pi over 3, then sine of 2 pi over 3, well, sine of pi over 3 would be root 3 over 2. If you rotate the triangle into quadrant 2, then that's going to affect the adjacent side, which we don't care about for sine of an angle, right? Sine of 2 pi over 3 is still going to be root 3 over 2. Times 4 would be 2 root 3. R squared equal 2 root 3 means that r is plus or minus the square root of 2 root 3. We've already done that, right? We're getting plus or minus 1.9 if we go nearest one digit. So on the pi over 3 axis, go out 1.9 units. Also go in the opposite direction, 1.9 units, and plot another point. If we let theta be pi over 2, the 2's will cancel there. Sine pi is 0, and so r would be 0. All right, this curve will pass through the pole then. All right, now what we're drawing is something that kind of looks like a figure 8 curve here. We call this a lemniscate. Now, in the last video, I was talking about lemniscans, and we looked at just kind of a general explanation about cardioids and lemniscans. A lemniscate is not a is different from a lemniscan. Okay, like the words sound similar, but they're two completely different curves. A lemniscate is a figure 8 type curve. Okay. And of course, this curve is symmetric to the origin. Remember what symmetric to the origin means. Any point that you plot x, y, negative x, negative y would also be there, if you're in rectangular coordinate form. Okay, and then problem 12 is the last one that I had in this list. In this problem, we're going to let theta be non-negative. If theta is negative, I'll mention what's going to happen there at the end. All right, so I'm just going to select some theta values. Like if theta is 0, r would be 0. Here's 0, 0 on the graph. If theta is pi over 4, 1/3 times pi over 4 would be pi over 12. Pi is a little bit bigger than 3, right? So pi over 12 would be a little bit bigger than 1/4. 0.26 is what I'm getting there. So on the pi over 4 axis, I need to go up 0.26 units and plot that next point. If theta is pi over 2, plug that in, times 1/3, you'd be getting pi over 6. That's going to be a little bit bigger than 1/2. I'm getting 0.52. So on the pi over 2 axis, you'll go out 0.52 units. If theta is 3 pi over 4, the 3's will cancel. Pi over 4 is 0.79 if you go nearest 2 digits. And so that's going to be my next point right here. If theta is pi over 3 is a little bit bigger than 1. Okay, on the pi axis, I need to go out about 1.05 units. If theta is 3 pi over 2, the 3's will cancel. Pi over 2 is 1.57 if you go nearest 2 digits. Okay, so here's that next point. If theta is 2 pi times 1/3, 2 pi over 3 would be 2.09 in decimal form. So on the 2 pi radial line, I need to go out 2.09 units. That'd be this point. So you can kind of see the spiraling thing happening. If theta is 5 pi over 2 times 1/3, that'd be 5 pi over 6. 5 pi over 6 in decimal form is 2.62, so that'd be that next point there. And then we're taking one more. If theta is 3 pi, the 3's will cancel. Pi is roughly about 3.14 if you go nearest 2 digits. So on the 3 pi axis, you're going to go out 3.14 units and plot a point. So what's going to happen is you're going to have this spiraling effect. We call this curve the spiral of Archimedes. Okay. If theta is negative, I would have like a double spiral thing. Okay. So that's the only difference. It'd be kind of like a double spiral graph if theta could be any number. All right. So that's some problems that I wanted us to graph by hand. And I guess the next thing would be to go to this sheet here that was in the notes also. This is kind of the last thing that I wanted to do. There's on this sheet, we have some special polar graphs. Okay, now I already talked about lemmasons and cardioids. Here's the general form of a lemmason. Okay, and what I have is the equation, and then some values of A and B, and then an appropriate viewing rectangle in order to see this exact curve that I've got drawn. Okay, so like suppose we wanted to graph this first curve here. In your calculator, we've been doing everything in rectangular mode, so there's also a polar mode that you'd go to, and if you go to y equals, then you can type in an equation in terms of r and theta. Okay, so I want to type in r equals 1 plus 2 cosine theta. The theta button would be the same button as the X button there. Okay, now the window, you'd want to go to that next. The conditions on theta, let's see, I'll just have theta going from 0 to 2 pi. You may need to adjust the theta values depending on the problem. Theta step, don't worry about that. That's a default setting that you won't ever need to change. Okay, and then x min, let's see, I'm going from -4 to 4 on the x-axis, also -4 to 4 on the y-axis. That's what I had indicated there. Okay, and then if I hit graph, we can see this lemmason with a loop that I've already got drawn there. All right. So you can try out some of these other ones too. We talked about a rose curve. One of the problems that I had shown you earlier was a 4-leaf rose. We drew that by hand. Okay, and when it comes to rose curves, there's going to be n petals if n is odd and 2 n petals if n is even. Here's just kind of the general form of knowing when you have a rose curve. R equal a cosine n theta, or r equal a sine n theta. Okay, and so in this problem, I had r equal 2 cosine 2 theta. So I would want to know that n is even, right? So you're going to have 2 times 2 is 4 petals. That's exactly what happened here. We have 4 leaf rows, okay? And so here's some more examples, like I said. All right, and then circles and lemniscates would be some more, special polar graphs that would come up a lot. Here's 2 circles. We looked at some circles earlier in the notes. Problems 5 and 6, we drew some circles by hand there. And lemniscate, we had looked at that earlier in this video. Right, here's a lemniscate, problem 11 that we had drawn by hand. Okay, now if we go to the last page there, on the other side of this sheet is just some more with polar graphs and technology. Now the idea with this sheet here is to have you guys basically just get some practice using your calculator, okay? Like, it's nice to be able to draw these polar graphs by hand, and we were doing a lot of that earlier here, drawing these by hand, okay? But we do need to know how to use a graphing calculator when we're faced with a curve that is more detailed, like the ones shown here. Okay, like I wouldn't want to draw any one of these by hand. That would be very brutal and time consuming. Okay, so knowing your calculator is handy. Just like knowing how to graph using your calculator is handy in when it comes to algebra and working with complicated curves there. So just for some practice, I have like a matching exercise. We're going to use the calculator, and of course make sure that you're in polar mode, and you're going to match the polar equation with the graph that's shown there. All right. So maybe since I'm already in the viewing rectangle -4 to 4, why don't I start with equation 2, and okay, so I need to type in r equals 3 plus sine of 5 theta. Another thing that I'd want to mention here just before we do that, make sure that you're in radian mode. If you're in degree mode, the graphs are not going to look at anything like what they need to be looking like here. Okay, so make sure that you're in radian mode for what we're doing. Hit graph. Okay, and we end up getting a star. Okay, so equation 2 is going to be matched with A that we see there. Okay, now if I change, by the way, if I change the conditions on theta, like if I were to go 0 to pi, let's say, I'd only look at part of the graph. Okay, or if I were to go 0 to 4 pi, in this problem I'd trace the star twice. Okay. Polar coordinates are different in that points can take on many different forms, and so that's worth mentioning here for this. Why don't we go to equation 4 next, and we'll graph that one. So if I go back to y equals, clear that out. We're looking at r equals e to the power sine theta, and then minus 2 cosine 4 theta. And we'll graph that. And we end up getting what looks like a butterfly there. Okay, so that's going to be matched with B. We call this it's a butterfly curve. Okay, obvious. But butterfly curve is obviously it looks like a neat curve there, but it's actually kind of a recently discovered curve, and in the grand scheme of things, I mean, a lot of these curves, these famous curves that I've been talking about, cardioids and lemnisons and circles and lemniscates and all that, like we've known about all this stuff for thousands of years. Okay, the butterfly curve, though, is kind of interesting. I think that was kind of first really discovered maybe about 40, 50 years ago, and a lot of work was done on that. So this, kind of a neat thing in comparison to the others there. why don't we do equation 5 next? Okay, I have to change theta so that we're going from 0 to pi. Let me just do that now so I don't forget. Go to window and we'll go 0 to pi. It'll automatically give you the decimal form there once you hit enter. And I want r equals negative sine of 5 theta, and then plus 4 sine theta. And hit graph. Looks like a heart. And so that's going to go with F there. Okay, why don't we go to we'll go to problem 1 next. I'll have to change theta needs to go from 0 to 4 pi, and then I also need to change the window there so that we're going from, let me change theta first, 4 pi, and then in this one it's a negative 1 to 1, I think was the viewing rectangle that we're using next. So then you can type in the equation. Alright, we got r equals cosine of 0.5 theta, and then times sine of theta. Okay, that's it. So hit graph. And it looks like a figure 8 there. So E would be that going to that one. If we do, let's do 3. So here's how I would do 3. If r squared is 1 over theta, then r would be equal to plus or minus the square root of 1 is 1 over root theta. Okay. So you can type in, two equations here. Let's go back to y equals. So here's 1 divided by root theta, and then go down to r2 would be negative 1 divided by root theta. And I think actually we need to change the window there. I guess we can already see what it looks like though, right? This is a double spiral. We call this a Litus curve, okay? And I guess I could change the, changing theta would be, producing more of the graph there. So the spiral of Archimedes would be one, curve that would belong in that family of curves. And then the last one there would be a flower if you were to check that. So just a matching exercise. But again, the idea with this worksheet is to just have you guys get some practice using your calculator. So, try out some of these on your own. Same thing on the first page, try out some of these in your calculator, and if you're not getting it, let me know. All right, at this point, we are now done with what I wanted to do in 9.2. Here's the answers to that matching exercise that we did there. The homework in section 9.2 is on page 600, and so be sure to look at those for me.